Chapter 9 review. All right, see what we have. It says the sequence A sub n is defined by A sub n equals A sub n minus 1 plus 3. Do you remember what this notation A sub n minus 1 stands for? It's the term 1 before the nth term. N minus 1, 1 before. All right, they say for n greater than equal to positive 2, and a sub 1 equals negative 1. So there's our first term, happens to be negative 1. They want to find the sixth term of that sequence. Well, one way is we can just start listing them. A sub n minus 1 plus 3, the previous term plus 3. So I just take negative 1 and add 3 to it, and I get 2. And then it would be 5, 8, 11, 14. 1, 2, 3, 4, 5, sixth term. Another way of looking at this is we're starting at negative 1, and this plus 3, we're just adding 3, 1, 2, 3, 4, 5 times. 5 times 3. That would also get us what the sixth term was. So it would be first term plus 5 of those plus 3s. Number 2. Determine the 25th term of the arithmetic sequence. There are a few formulas that you want to make sure that you have memorized. The nth term of an arithmetic sequence. A sub 1 plus, anybody remember?
N minus 1 times D.
N minus 1 times D. These are common difference. So let's figure this out. We know our first term is 5 on this one. Our common difference, what are we adding each time?
Negative 3.
A negative 3 is being added each time. So we should be able to figure out what the 25th term is. A sub 25 would be the first term, just using our formula over here, 5, plus, well, 25 minus 1 is 24, so n minus 1 is 24, times our common difference of negative 3. I'll let you do the math.
Negative 67.
Negative 67 would be the 25th term. So there's kind of our first formula, I guess, to memorize, is the sum of an arithmetic series. Number 3. For questions 3 through 5, determine whether the sequence converges or diverges, and if it converges, give the limit to it. So they have 3 over 1, then 4 over 2, then 5 over 3, then 6 over 4. Well, we may start to look at the values and try to figure out, is this thing getting closer and closer to a number, or is it not getting closer and closer to a number? So if first number is 3, then 2, then 1 2/3, and then 1 1/2, and
7 over 5.
does it appear to be converging or diverging?
It's closer and close to 1. If it's 1,000 over 1,000, it's just really close to 1.
If I looked and tried to write a little formula, if I called it n on the bottom, first term, second term, it's n plus 2 on the top. And we can tell, if you remember, it's like those horizontal asymptotes. I'm going to compare the degree. If the degrees are the same, then I divide the lead coefficients, 1 and 1. 1 divided by 1 is 1. It converges, and it converges to 1. It's getting closer and closer to 1. 1,002 over 1,000. Jackie, you were talking about using 1,000. That's really close to 1. 1,000,002 over 1,000,000. That's getting really, really close to 1 as you keep going. Number 4. N squared, and this one gives us the formula, so I'm going to use that technique I did on the second part. N squared plus 3 over n plus 2. Okay, well if I have a numerator greater than the denominator, then it diverges. It has no horizontal asymptote if I graph this thing. This is just diverging. Number 5 gives us the formula. N to the negative first, I would probably think of that as 1 over n. N to the negative first is 1 over n. Before I tell you anything, what do you think? As n gets bigger and bigger and bigger, am I converging to something or diverging? I'm converging to what? 0. I'm getting closer and closer to 0. 1 over 1, 1 over 2, 1 over 3, 1 over 1,000, 1 over a million. I'm getting closer and closer to 0. And I'll say the other rule here next. We converge, it converges, and it's converging to 0. Well, my top degree is 0, bottom degree is 1. If the degree of top is less than the bottom, it's 0. Y equals 0 is the horizontal asymptote. Converges to 0. Number 6. Find the sum of the first 6 terms of the geometric sequence. 2, 10, 50, ... Sum of a geometric. We'll probably want to write down some other formulas before we... This is really a couple formulas into the chapter. Sum of a geometric. A sub 1 times 1 minus r to the n divided by 1 minus r is the formula. Let's write a couple of other formulas down. That's r to the n up there. I need to reorient my board, I think. On an arithmetic, we have a sum. Sum of an arithmetic. I'm trying to remember how this book did it. If they do n over 2, a sub 1 plus a sub n, this is one way of writing it. A sub 1 plus a sub n. I have to look back and see if that's how this book did that. It's back on 700. Where is it? Can't even see it now. Sum. Back too far. Oh, this book wrote it this way. N a sub 1 plus a sub n divided by 2. Either way. So there's the sum of the arithmetic. Now, on a geometric, the nth term of a geometric, a sub n equals a sub 1 times r to the n minus 1 power. So there's another formula that we have. So there's the sum of the arithmetic in there, but those are the 2 geometric ones. All right, so number 6, they're wanting us to find the sum of the first 6 terms of this thing. So we are going to be using this sum formula right there. So if we're going to find the sum, a sub 1 is 2, times 1 minus the common ratio. What are we multiplying by in this thing? 5. Raised to the 6, I want the sum of the first 6 terms, so raised to the n power, raised to the 6, divided by 1 minus the common ratio, which is 5. 1 minus 5. I wonder if they took this. Oh. Try it out on your calculator, I guess. What do we get for that sum? So -4 on the bottom. I mean, you could do some simplifying first, but.
7,812.
7,812 should be the answer you're getting from that formula. So 4 formulas. We had the first one right back over here, the nth term of an arithmetic. We have an nth term of a geometric, and we have the sum of a geometric, sum of an arithmetic. We need to know those. We also have an infinite. Sum of an infinite geometric is a sub 1 over 1 minus r, as long as the absolute value of the common ratio is less than 1, it works. Sum of an infinite. So here's another formula we also had. Number 7, write in expanded form summation. K equals 1 to 4, is that what that is? Summation. K equals 1 to 4 of k cubed minus 2k. So this is write it out and figure out the answer. We start with a k of 1. So we substitute our k there and there. So 1 cubed minus 2 to the first. Well, that's 1 minus 2 is negative 1. Plus. Then we go to a 2. 2 cubed is 8. 2 squared is 4. 8 minus 4 is 4. Plus. And we go to a 3. 3 cubed is 27. 2 to the third is 8. 27 minus 8 is 19. Almost the wrong number. Plus, what are we up to, a 4? 4 cubed is 64. 2 to the fourth is 16. 64 minus 16, 48. And that's where we stop. Start at 1, stop at 4. If we add them up. 70. So knowing how to do summation notation, another thing we did. 8 and 9 you may cross off. We did not do this induction. Number 10. Oh, binomial stuff. Binomial expansion question is what number 10 is. How many terms, one of the patterns, does a plus b to the 99th power have in expanded form? One of the patterns. Do you remember? 100. There's one more term than the number of power it's on. You may want to look back over on the binomial expansion. There's a whole bunch of patterns. So that question just happened to come from one of those patterns. And they can ask all sorts of strange questions on tests. 11. Find the expanded form, 3u minus v to the 5th. Careful that your v's and u's don't look the same. All right. I'm going to start out with the coefficients. I know it starts with a 1, and the next one is a 5. How do we get the coefficients? We can use the combinations. They're called the binomial coefficients. This is 5, because it's the 5th power. This is 5, choose 0. This is 5, choose 1. The next one is going to be 5, choose 2. I don't know, what is that? You can try that. Combination of 5 things chosen 2 at a time. 10? Now, I could keep on doing. It's 5, choose 3, 5, choose, but I'm going to use one of those patterns. Since it's to the 5th power, how many terms are there?
6.
There are 6. I have the first half already done. So I know the second half is symmetrical. 10, 5, 1. 10, 5, 1. So 1, 5, 10, 10, 5, 1. Must match. So is there another way other than those binomial coefficients, that 5, choose 0, 5, choose, is there another way to get those numbers?
Pascal's triangle.
Pascal's triangle is another way to get the numbers. 1, 1, 1, 1, 2, 1, 1, whatever it is. 1, 3, 3, 1. Pascal's triangle is another way. All right, so let's start with the u. U is raised to the what power for the first term? Fifth power. And then I'm going to do all my U's. And then it goes, ooh, what about the 3? 3U is raised, isn't it? 3U is raised to the fifth power. And 3U is raised to the fourth power. I'm just going to run all the way down doing those. Oh, I messed up somewhere. 5, 4, 3, 2, 1, 0. Negative U. How about in the first term? Do I have a negative U?
No.
It's raised to the 0 power, which equals 1. I don't have to write it. But then in the next one, that negative U is to the first. Oh, it's a V. I was the one that told you don't mix up your U's and V's. It's a V. Negative V squared. Negative V. Then we're adding all these things together. Should end up to the fifth power, just like the first one started with the fifth power. Now we have to simplify each of these terms as we go along. I can do powers first. What's 3 to the fifth? 243? So 243 U to the fifth. All right, 3 to the fourth.
Okay. 81.
81 times 5.
405.
405, and times a negative here.
Yeah.
So it's negative 405. Then my U is to the fourth.
V.
And V. All right, and the next one, now my sign is going to be plus here because when we square a negative, it goes positive. 3 to the third is 27 times the 10, 270. U is cubed, and V squared, because we square the negative, becomes positive. All right, this next one's going to be a negative term, because negative V to the third is a negative answer. 3 squared is 9 times 10, 90. So negative 90, U squared, V cubed. And remember, if we add up any of these, 3 and 2 are 5, 2 and 3 are 5, 4 and 1 are 5. They always equal the same power. That's another pattern. All right, the next one, a negative to the fourth is a positive. Just 5 times 3, isn't it? 15 U V to the fourth minus V to the fifth. Our negative to an odd power is a minus. There it is. So we expanded it. Number 12. How many different, hands of 5 cards can be dealt from a standard deck of 52 cards? So here we ran across several other things that we had. In factorial is one thing we learned. Remember what factorial is? 7 factorial, 7 times 6 times 5 times 4. This is the number of permutations if we have n things. How many ways we can order n things? If I had 3 students, how many ways can I order 3 students? 3 factorial. 6 ways. Permutations, a permutation, n things chosen r at a time. Those are also order, but if we're taking a smaller number from a group. Combinations, what's the difference with a combination compared to a permutation? Order doesn't matter. Order doesn't matter there. All right, so let's see what we had. How many different hands of 5 cards can be dealt from a standard deck of 52 cards? Can you tell me how we will set it up to answer that question? It is a combination of 52 cards, and we are going to choose 5. How many different ways can we choose 5? And order doesn't matter in a hand of cards.
598,560.
There you go. 2.5 million different 5-card hands you can have for 52 cards. Number 13. How many different computer passwords consisting of 6 uppercase letters, so they're telling us it's just uppercase, are possible if no letters are allowed to repeat? Okay, any ideas? Number 13.
26 times 3.
Okay, well, how many computer consisting of 6 uppercase letters? So there's one way to do it. The first time you have how many choices, the first letter?
26.
You have 26. And the next one?
24.
And we have how many letters? 6 of them?
Yeah.
1, 2, 3, 4, 5, 6. Multiply that together.
A lot.
Can you be more specific on that answer?
165 million. 765,600.
600? Now there's another way of getting this answer. This is a permutation, because the order we put the letters is important. We are from 26 letters, we are going to be selecting 6 of them, and order is important. Try that on your calculator. A permutation of 26 taken 6 at a time. Does it give you the same answer? Good. A couple of ways you could have gotten the right answer there. Number 13. Number 14. What is the probability of a 6-digit bank account number chosen at random have no repeated digits? Okay, now to do probabilities, we always have a fraction. The number of ways we can get what we want on top over the total number of ways something can happen. So let's see what we want to do. 6-digit number. How many ways can we choose 6 digits? Does order matter?
Doesn't.
On a bank account number, would an order matter?
Oh, this one.
Yeah, the number 123 is different than the number 321. So order matters. So how many digits can we choose or select from when we're talking about numbers? How many digits are there? There are 10. 0 through 9. So there are 10. So the number of ways I can get what I want, a permutation of 10, selected 6 at a time. We want to get 6 digits, and we can choose from 10 of them, and the order matters on the bank account number. So that's the number of ways we can get what we want. So on the bottom, what do we have? The total number of ways of numbers. It's going to be like how we started on 13. The first number you select, how many numbers do you have to choose from?
10.
10. The next number you select.
If no repeat is 9.
Now this is the total number of ways you can select 10 numbers. The next time, 10 digits, the next time you have 10 as well. This isn't no numbers are repeated. This is the total number of ways you can do it. This is 10 the first one, 10 the second, 10 the third, through all 6 of them, 10 6 times. Or 10 times 10 times 10 times 10. That's the total number of ways you can select 6 digits. You have 10 choices the first time, 10 choices the second time. That you can turn into a decimal formula for a probability. Take it to several places.
15.12.
You have your decimal in the wrong place.
No, I use 15.2.
Oh, percent. You're telling me in the percent. 0.1512. Generally, we prefer not to write it as a percent. I would give you the points if you did. 0.1512. You're right, 15.12% chance of being able to do that. Number 15, 2 digits. All right. Each between 0 and 9 inclusive, which means we can include 0 and we can include 9, so there are 10 digits here, are chosen at random. Repetition is allowed. What's the probability that the first digit is even and the second digit is less than 4? So we have two things going on. Let's get the first thing. Probability the first digit we choose is even. What's that probability?
50.
It's 5 out of 10, right? 50%. There are 5 even out of the 10. And remember, if we have and going on, we multiply. If we have something or something else going on, we add. But we want to do this, and the second digit is less than 4. So there are 4 numbers out of 10. There you go. Do the math on that. You can give it to me as a decimal. 0.2. 20%. 0.2. There's the probability that thing will happen. So we just have to, on this probability, figure out the number of ways we can get what we want over the total number of ways that can happen. Questions 16 through 19 refer to the following data set. Number 16, construct a stem plot. All right, so let's see. If we're doing a stem plot, we look at this data. What's our smallest number?
8.
8 something, isn't it? And it goes all the way up to...
12.
Oh, 14. There's a 14.3 down there.
Oh.
So let's set up our stems as 8, or let me go ahead and do it. 8, 9, 10, 11, 12, 13, 14, all the way up here. Remember, if they say a split stem plot, then we'd have 8.0 to 4 and 8.5 to 9. Splitting the stem. That's what they mean. All right, now just start going down the list. I'm filling it in. 9.6. And we'll see if yours looks like mine when we're done. There we go. Stem and leaf plot. We would label it. This is our stem, and here's our leaf. Or our leaves, I guess. 16, construct a stem and leaf plot. There it is. 17, in the space below, construct a frequency table for the data. And then we're going to draw a histogram, and it says using the intervals of 1. So if we are going to do a frequency table... Frequency table is the count of the number of times it falls in a category. And it says do an interval of 1. So 8.0 to 8.9. So here's our interval. And then this will be our frequency, and we'll just make tally marks. So let's see, 9.0 to 9.9. The stem and leaf plot makes it easy to do the frequency table. How many 8s do we have? 4. We've got 4 of them. I'm going to do it as tally marks. You could write the number 4. 2, was there 5? 2, 1, 0, 1. All right, and when they gave you a chart. I'll have to do for the histogram. There's our histogram. Looks something like that. Yours will be better because you have nice. There we go. Fill it in. 18. Find the mean, median, mode, standard deviation. If necessary, this is ran to the nearest hundredth. Well, here we go in the calculator. Stat. I'm going to clear out. Let's see, stat, calculate one variable statistics. So, what's the mean? 10.32. The median? What's the median? 10.3. Mode. What does mode mean? I don't think this one gives us the mode. The most frequent. So what's the mode? Is there a mode, maybe? 8.9. 8.9 is the most frequent. Standard deviation. I need to find my calculator again. Which one do we use? The standard deviation thing. Do you remember?
Something.
We use sample.
No, not simple.
Okay, the question is it a sample or is it a population that we are looking at on this one? It's the population. We have all the numbers. I mean, it's not a sample from, rooster hens or something like that. And so this is the number right there. So nearest hundredth, standard deviation, 1.52 would be the answer. Let's see, I haven't written down any of these. The mean was 10.32. The median was 10.3. Most frequent was 8.9. Standard deviation, 1.52. 19. Construct a boxplot for the data, then explain why a modified boxplot would or would not be different from your drawing. All right. We'll draw it on our paper, but we're going to do it from here in our calculator. So we'll do a stat plot. Number 1, turn on So mine's already on the right thing. Box and whisker plot from list 1. So let's hit the window for a minute. Now our x minimums, those are the x values of it. What did we go from 8 to 15 essentially? 8 to 15, minimum, maximum, scale of 1 maybe. Now the y is just going to put it in our window so we can see it, so probably -5 to 10 is just fine. Uh-oh, invalid dimensions. What did I do? Is yours working? I can't figure out why mine's not plotting. Stats and valid dimensions. We're going to pause the recording a second. All right, I had 2 plots turned on. That's why mine wasn't plotting. Now, you've got a little line down there. So if I hit trace, 8.1, I mean, I would graph yours out. When you do your graph, you have your line, 8, 9, 10, 11, 12, 13, 14, 15, and then just draw the stuff off, putting it in approximately the right spot. So 8.9, quartile 1 there, the median, quartile 2, 10.3, 11.3. Now we have another question to answer. As you're drawing that out, it talks about a modified box plot. We modify our box plot if we have an outlier on this. And so we did have this big number, 14.3 out here. How do we decide if we have an outlier? If it's greater than 1.5 times the interquartile range, it's going to tell us if we have an outlier or not. So our interquartile range is between quartile 3, that's 11.3, and quartile 1, 8.9. So 11.3 minus 8.9. 1.5 times 11.3 minus 8.9. What do you get for 1.5 times the interquartile range?
3.6.
3.6? So what we do now is we say, all right, this quartile 3 was 11.3. We're going to add 3.6 to it. Where does that take us? 14.9. Is 14.3 inside that, or is it an outlier? It's inside it. So there would not be a modified box plot or box and whisker plot. Not modified. No outliers. You know, outliers can be too small, too. I mean, we could be going on the small side as well as the big side. But there's no outliers. Is that it? As far as this, that is it. So we remember, of course, that there's a whole chapter in the book of which they did not select all the possible questions.